Hey, welcome back to Fat Mama Physics. In this video, we are going to talk about electric potential energy. Oof, so this is 5.1b continued. We got two questions here, which I'm going to do together because it talks about the amount of work done bringing charges close to charges. And especially if you got positive to positive charge, negative to negative charge, that's pretty hard. If you have like charge, because we know that like charges repel, unlike charges attract. So let's get started. Example 1. How much work must be done to bring a 4 microcoulomb charged object to within 1 meter of a 6 microcoulomb charged object from a very far distance away? Okay, so let's draw a diagram first. We have a positive charge here, which we're gonna keep at this space. So it looks like we're bringing the 4 microcoulomb charge from far away. So this will be the 6 microcoulomb charge. To be honest, it doesn't matter, but calculation-wise, it doesn't matter. But it's good to kind of get a good idea. And this other charge, which is smaller, which is the 4 microcoulomb charge, we're going to take it from a very far away place. And usually what that means is it starts off with a distance of infinity. So we're taking this from very far away. And what we know about charges, if they're really far away, they don't really feel each other. So we say that the potential energy at this spot between these two charges is about 0 joules. But we want to move this guy here, which is 1 meter away from this guy. Okay? And if you think that, oh, then that's going to take a lot of work to do. Yeah, you're absolutely correct. It's going to take work to bring that potential and bring those two positive charges with a very high amount of potential energy between the two. So if this electric potential energy is 0 far away, then essentially the work done to bring this positive charge to 1 meter away from the 6 microcoulomb charge is going to be exactly what we learned before, KQ over R, which is the electric potential energy between these two charges at that point. Okay, so we're going from 0 all the way to whatever they feel. However they feel each other at that point. So when I calculate this, EP is essentially just K, big Q, small q. It doesn't really matter. They're just two charges divided by the distance of separation at that point, which in our case is 1 meter. There is no square here, so you don't need to forget the square, but don't put in the square because that will change the answer too. Okay, so this is 8.99 times 10 to the power of 9. And then for the two Q's, you just substitute in the charges. Notice I've gone a little lazy with my penmanship and the units. And the 1 meter away is, it's just 1 meter. So you don't have to multiply by anything. It's already in meters. Putting all of this in the calculator, I get 0.21576. Don't forget when you actually put in 4 and 6, don't forget to multiply by 10 to the power negative 6, since it is a micro. I just got lazy there, sorry. And this is going to be positive. This is, looks like 2 sig figs, actually. So 0.22 joules. Okay? And guess what? Since these these positive charges don't like one another, it's actually going to take work to put them together. So in fact, you're going to get a positive number here, which also reminds me, when you do calculations for electric potential energy, and eventually for electric potential as well, for the positive and negative charges, you do and you should put in the signs, because the energies that you find, these are all scalars. Unlike talking about electric field and electric force, we're dealing with vectors. So you can draw out your diagram. After you've drawn out your diagram, you've accounted for the direction already with the charges. So when you calculate it, you don't need to put in the charges. You can just work with the magnitudes. But when we talk about energy in terms of scalar, where there is no direction involved, it is important that we do put in the positive and negative charges into our equation to give us our final answer. So you'll notice in example 1, for the positive charges, we put in positive numbers. We didn't put in any negatives. And as a result, it gave us a positive number. This has significant meaning because it actually takes work to put two of the same polarity charges together, two positive charges together. That's going to take work. You're going from a low energy state between the two charges to a higher energy state. So work has to be done. Work has to be done to the system, meaning that the total energy in your system increases. Okay, so if I had to draw this as a diagram, energy, you have to do work on this energy for the system's energy to go up. And in this case, it does go up. The electric potential energy between these two charges have gone up as a result. Let's contrast this one with example 2. How much work must be done to bring a negative charged object to within 0.5 meters of a 5 microcoulomb charged object from a far away distance? So the one that is stationary is a positive charge, okay? And then the one that's far away is a negative charge. So we want to bring this guy from somewhere very far away, and it doesn't matter if it's a positive or negative charge. We say that when two objects are very far away, they're not really interacting as much. So the electric potential energy is roughly 0. But if we put this negative charge very close, and in fact, it's gonna like that. The negative charge is gonna really like to be near that positive charge. So in fact, if I let this negative charge go, if it's at infinity, then maybe not so much. But if you tip over the balance a little bit, or if you put a negative charge anywhere close to a positive charge, or to some vicinity, then that negative charge is going to want to go to the positive charge because they are attracted to one another. That has meaning, which we'll talk about in a second. So after it reaches this spot, this is 0.5 meters away, essentially we're going to get some potential energy here, which is KQQ over R again. And whatever we get there versus the electric potential being 0 far away, that's the amount of work that has to be done. Okay, so essentially I just have to calculate EP at the 0.5 meter mark since it's 0 at infinity. For K, it's just 8.99 times 10 to the power of 9. And remember, we're dealing with scalars, so we need to put in the positive and negatives. So the 5 microcoulomb, sure, I can leave it as that. But for the negative 7 microcoulomb, I will put in that negative sign, 7 microcoulombs. And of course, I need to put in times 10 to the power of negative 6 in my calculator later on, all over 0.5 meters, which is the distance of separation. I get negative 0.6293, which is going to round to 2 sig figs, negative 0.63 joules. Okay, and hey, we got a negative sign there. So let's talk about why this is negative. So if I have a positive charge and a negative charge far away, well, I mean, sure, the potential is 0, but any tipping over of that electron, even some amount of... If I release a negative charge somewhere close to being far away, or some distance away from this positive charge, this negative charge is going to want to come towards that positive charge. So, not just come towards, it's going to accelerate towards a positive charge. So in fact, it's going to gain kinetic energy as it approaches the positive charge and potentially smashing itself against. But anyways, it's going to accelerate. So the negative charge, in fact, is going to gain kinetic energy because that potential energy that it has far away from the positive charge is going to will get converted to kinetic energy. So I almost think of it this way. It's if you're taking that negative charge and you're bringing it closer to that positive charge, then you've kind of taken away the potential for that negative charge to gain kinetic energy, because you're just taking it there and you're just placing it here. So there was you basically took away that chance for that negative charge to accelerate, to gain kinetic energy. Or you can think of it as the amount of energy that these two charges would have far away is going to be higher than the potential energy that these two charges would have close together. So you're going from a high energy state to a low energy state. In which case, your system, which is these two charges, is going to lose energy. If it loses energy, we often associate that with a negative sign. So in that sense, work, we call that doing, by definition, we call that doing negative work on the system. A similar case would be if you take 1 kilogram mass. So thinking, so it's kind of like lifting weights. You're taking that 1 kilogram mass and you're kind of and you're lowering it at a constant rate. So again, it's kind of like doing negative work, because you're working in the direction of the acceleration due to gravity. And in this case, you're working in the direction of the electric field. And again, I think of it as you taking away the opportunity for this object to be able to accelerate or to gain kinetic energy. Yes, the concept of the negative work done it can be a little bit confusing. Ultimately, think about the change in energy of your system. If the energy goes down, if the energy level decreases, then think of energy leaving your system associated with negative work. If the energy of your system increases, think of that being work being done positively to the system to increase this energy level. Okay? Here we go. Example 1 and 2. Thank you for watching. Stay tuned for more electrostatics. Van Mama Physics signing out.